Up till now, in previous part, we have seen the various software process models. Now we'll look into the product and process details of the clean room software engineering. The product is what we are actually building. What's our solution to the problem at hand? Half of engineering is making sure you are building the right product and have the ability to actually build it. For software engineers, that means coming up with a software solution and being able to code it up properly. The hidden side of engineering is the process, which means how we are actually building our product. Products don't just result from a single all-night coding session. We need to make sure we are following a process that lets us create that product in the most efficient and effective way possible. So now, as we have understood the difference between product and process, we will make use of this in later sections. We'll look into clean room software engineering. Clean room software engineering is a practical application of mathematical and statistical science to produce high quality software in an economical manner. The clean room name was borrowed from the hardware clean rooms of the semiconductor industry, where defect prevention rather than defect removal is pursued through rigorous engineering processes. The emphasis in clean room is on the development of software that is correct by design, followed by certification of software quality in testing. Clean room software engineering is designed to achieve two critical goals. First one is a manageable development process, and second one is no failures in use. Let us see the details of a manageable development process. Clean room methods enable managers and technical teams to maintain intellectual control of software development projects. Intellectual control requires that at each step in the development, the status of work in progress is absolutely clear. Intellectual control requires teamwork based on well-defined engineering processes. It results in managing complexity, reducing risks, avoiding rework, and meeting business objectives for schedule and budget performance. No failures in use. Post-production defect correction is an institutionalized and accepted process in many software organizations, involving substantial operations that drain productivity and profitability. Most software failures are avoidable. Software failures are the result of ineffective specification and development practices that permit introduction and survival of defects, and testing practices that permit defects to remain undetected, only to be discovered in field use. In clean room, development teams use rigorous specification, design, and verification practices coupled with testing practices in approaching the goal of zero defect. We'll talk about the clean room team operations. Clean room team performs three principal operations. Number one, system specification. Number two, development. And number three, certification. Teams are generally small, in the order of 3 to 8 people, to minimize coordination and to simplify communication. Clean room software engineering is characterized by three principal technologies. The first one, the incremental development and the statistical process control. Second one, function-based specification, design and verification. And third one, statistical testing and software certification. These technologies can be used separately or together and can be introduced in any order to improve software practice. Incremental development involves a series of smaller cumulative development phases. Each pass is cumulative, involving all work in previous increments plus some new work. Incremental development is essential to the ability of the development team to maintain intellectual control of a project. Team members thus focus on only a portion of the work at any given time rather than trying to keep all the things in mind at once. Another principal technologies is the function-based specification, design and the verification. Clean room employs development methods that are both theoretically sound and highly practical. Specification begins with an external view called as a black box, is transformed into a state machine view called the state box, and is fully developed into a procedure called the clear box. These distinct but behaviorally equivalent forms are known collectively as the box structures. Box structures are object-based and support key software engineering principles of information hiding and the separation of concerns, which we have previously seen in AOSD. Correctness verification. In box structure specification and design, a black box is defined to record required behavior. Then a state box is refined from the black box to define required state data, and finally a clear box is refined from the state box to define required processing. All cleanroom developed software is subject to functional correctness verification by the development team prior to release to the certification test team. Third principal technologies is the statistical testing and software certification. Cleanroom testing methods are grounded in the fundamental statistical principle that sampling must be used when a population is too large for exhaustive study. A usage model is developed to represent all possible system uses, and test cases are generated from the usage model. Because the test cases are a random sample of the population, valid statistical inferences can be made about expected operational performance of the system. The figure indicates the cleanroom development process. You can see over here there are 4 phases: software specification, development, correctness of verification, and the certification. You can see the first principal technologies is the incremental development, then functional specification, and third one is the statistical testing and the certification model. To summarize with, prescriptive process models have been applied for many years in an effort to bring order and structure to software development. Each of these models suggests a somewhat different process flow, but all perform the same set of generic framework activities, which are communication, planning, modeling, construction, and deployment. Sequential process models such as waterfall and V models are the oldest software engineering paradigms. They suggest a linear process flow that is often inconsistent with modern realities like continuous change, evolving systems, tight timelines in the software world. They do have applicability in situations where requirements are well defined and stable. Incremental process models are iterative in nature and produce working versions of software quite rapidly. Evolutionary process models recognize the iterative, incremental nature of most software engineering projects and are designed to accommodate the change. Evolutionary models such as prototyping and the spiral model produce incremental work products or working versions of the software quickly. These models can be adapted to apply across all software engineering activities from concept development to long-term system maintenance. The concurrent process model allows a software team to represent iterative and concurrent elements of any process model. Specialized models include the component-based model that emphasizes component use and assembly, the formal methods model that encourages a mathematically based approach to software development and verification, and the aspect-oriented model that accommodates cross-cutting concerns spanning the entire system architecture. Personal and team models for the software process emphasize measurement, planning, and self-direction as key ingredients for a successful software process.